I will talk today about AI in energy, challenges and opportunities. So just before I start, a few words about myself. I'm a co-founder and the chief scientist of Immubit, which along the way I'll tell you a little bit about. My area of expertise is the mathematical foundations of AI, specifically neural networks. I'm a professor of computer science at Tel Aviv University. Before that, I was in Princeton, mathematics and computer science. Before that, PhD at the Hebrew University in computer science, master's in computer science, and before that, I was at the Technion, electrical engineering and mathematics. I was fortunate to receive several awards for my contributions to the foundations of AI. Specifically, I was the fourth person in the world to get a Google doctoral fellowship for these contributions, and also got a Research Scholar Award by Google that was given to 11 people. Besides the academic record, I have about 2 decades of experience applying AI to industrial systems. So for the last close to a decade now, it's been to the energy industry. Before that, aerospace and defense, worlds like that. All right, so AI needs no introduction these days, right? We all know that it's changing the world, and it's also having impact in the energy industry. Some applications include predictive maintenance, right? Anticipating in advance when equipment's gonna fail or deteriorate. You could use it for forecasting demand, okay? Being ready in advance, making decisions more optimally. You can also use it in upstream, various applications, for example, image interpretation. These are all applications that have been around for a while. A set of applications that's newer or now kind of emerging are the use of generative AI tools for kind of helping with everyday tasks. This is relevant to pretty much all the industries, and energy is no exception. And there will be discussions around this today, I'm sure. All right, a very, very important point to note, which might be obvious to most of you, maybe not all, is that AI is not a well-defined term at all. It's like saying technology. And I believe that in the future, when we look back and think of how people refer to AI as some specific solution, it'll look funny. Maybe the way we look now at the 19th century, where people referred to technology as a way to solving a problem. Today, it's clear that there are various types of technologies, very different from one another. I believe the same will be with AI. From a more professional standpoint, AI refers to a collection of machine learning frameworks, and they vary significantly from one another in terms of how powerful they are, what they can do, how complex it is to implement them. On the lower end, there's a framework called supervised learning. Then there are various other frameworks, then something called self-supervised learning, more frameworks, and at the very end lies something called reinforcement learning. We will talk about all 3 of those. What's important to note at this point is that most of the applications in the industry are on the lower end. Typically supervised learning, sometimes other things, and now self-supervised learning a little bit also. But reinforcement learning, there are very, very few applications. There's a lot of unrealized value there. What's supervised learning? Supervised learning is a paradigm for designing a mapping from inputs to outputs. Okay? So, for example, the possible inputs could be time series, taken on a minute-by-minute basis, representing maybe some temperature from some unit. And the possible outputs could be categorizations, like red means there's a problem, B means everything's good, and C means warning. A mapping just produces an output given an input. And the traditional way to design these things is through domain knowledge, through first principles. Okay, we know something about that unit, we know how its temperature is supposed to behave, and we come up with a set of rules that ultimately gives us an estimation of what the label for this input should be. So we managed to get pretty far this way. We did a lot of things in the industry and beyond. We built the internet, we got to the moon, we did a lot. Apparently, there are problems that are very, very difficult to solve this way. And supervised learning offers a fundamentally different approach, and that is to learn from examples. Okay, so what you do, instead of crafting a specific mapping, you define a big set of possible mappings, a mapping class. It's usually parametric. There are infinitely many mappings here. And you collect training data, which are examples of an input and the corresponding output. Okay, so if the system is given this input, I want it to produce B. If it's given this input, I want it to produce C, and so forth. Right? Then you take these two things, feed them into what is called the training engine, which at the end of the day boils down to a search for the member of the mapping class that best agrees with the training data. You take that thing and you apply it in the world. That's supervised learning in a nutshell. Okay? This accounts for the vast majority of applications in the world in general and specifically in the energy industry. Self-supervised learning is something that's closely related but different, or you could see it as a special case that entails various challenges. And the idea here is to design a predictor of sequence elements. And to be more concrete, usually the case is that you want to create a predictor that is given a sequence and will predict the next element of that sequence. Okay? That's what you're trying to achieve, some kind of predictor. And the way that you generate it is through supervised learning. And now these examples that you use for training, the labels don't come from a human annotator, they come from the data itself. Okay, you extract sequences from the data itself. So you have a predictor class, and now your training data are these sequences. The input is a sequence, x1 to xt. The output is the next element of that sequence. And you can cut off these examples from a long stream of information, kind of an infinite series. Then you take these two things, feed them to the training engine, and you have yourself a learned predictor. Okay, that's self-supervised learning. And this is the core engine behind generative AI these days. Okay, it's basically this. ChatGPT, it's self-supervised learning. It's a predictor that predicts the next element, and it's trained over the entire internet. And the sequence elements are text tokens. You can think of them as words. You just take a predictor, train it to predict the next word over the entire internet. That's it. That's 95% of ChatGPT. Then at the end, there are a few additional tweaks. Okay? And it's not just ChatGPT. It's also other models that you have here, like Gemini, Claude, Pi, and also it's not just the text aspects of these models. It's also the imagery ones and the videos and everything you've seen. Okay, so self-supervised learning is very, very useful. Reinforcement learning is something that goes way beyond both supervised learning and self-supervised learning. In reinforcement learning, we're not designing a mapping or a predictor. We're designing a controller that operates in a dynamic environment. Okay, it doesn't just receive input data and outputs some single element. It actually needs to make decisions. Okay, so for example, if we had a robot that is walking in this auditorium and trying to clean it up, the robot would have sensors through which it can sense the environment. It has motors so it can move, and it's trying to achieve some long-term goal, which is to clean this place up. If everything stands still and nobody moves, it might be easy, but if we start walking around or spilling coffee, or I hope there's nothing like that here today, it's a more challenging problem, and the robot needs to somehow understand what's going on and adapt and make decisions that implement some strategy towards its long-term goal. That is the most basic example of reinforcement learning. Okay? Formally, the framework looks like this. There's a controller and there's the environment. The controller observes a state. That's a description of the environment status. So in the case of the robot, it will be its sensory inputs. The environment's this auditorium, and the state is the sensory inputs that the robot sees. Then the robot takes an action, some operation. Okay, so that would mean moving its motors in some way. Then the controller receives a reward, which is an indication of the goodness of the environment status. So if this hallway is cleaner, it'll be a reward of +1. If it's dirtier, it'd be -1. That's one single iteration. State, action, reward. this repeats again and again and again. And the agent's, the controller's objective, in our case it's a robot, is to maximize the reward over time. Okay? This is a very, very general framework. You can think of our lives as a reinforcement learning problem. We have 5 senses, we have who knows how many muscles, so we sense the environment, we take actions, and for a given definition of a reward, like emotional well-being or money in the bank, you define it, maximizing that over time is a reinforcement learning problem. And so in some sense, this is the essence of intelligence, being able to adapt to a dynamic environment, make decisions, implement strategies towards long-term goals. And all the rest of the learning frameworks can be seen as special cases of this. That's reinforcement learning. Conventional methods for reinforcement learning that you will find in the literature rely on 2 basic assumptions. First assumption is that you have an accurate mathematical model of the environment. And the second assumption is that you can do trial and error. Okay, so the robot will start out not being very effective, and over time, it'll learn from its mistakes and improve and improve and improve. Okay? So those are conventional reinforcement learning methods. Those are the assumptions that are relied upon. If you think of applications of reinforcement learning, there are not that many that are famous. Here are a few. Beating people at computer games. It's been several years now since reinforcement learning has managed to solve many, many games and play in superhuman level of performance. Beating the world champion at Go. I'm sure many of you have heard of this. These 2 examples are relatively simple in the sense that it's pretty easy to have a mathematical model of the environment, and it's pretty easy to do trial and error. One of the only examples in the real world is self-driving cars. It's not yet in mass use, but it is advancing, and in certain settings, it's even driving better than humans do. And in order to meet the 2 assumptions that mentioned earlier, a lot of money and a lot of resources were invested. Okay? A lot of smart people building a lot of mathematical models of roadways and things like that, and a lot of test cars with a lot of test drivers doing trial and error. And then if the algorithm, for example, wants to make a mistake, drive off the road or something, the test driver would take the steering wheel and there'd be a reward of -1. Okay, so these are some of the applications of RL. If you imagine perfect RL in the energy industry, then the amount of things you could do is pretty much infinite. Here's just a few examples. One is process optimization. Okay? You could imagine RL optimizing your processes, improving the yield, reducing emissions, making them run much more robustly and much more profitably. You could imagine using RL for decision-making in midstream, right? Like railroads, pipelines, a lot of decisions there, where to transfer and how to. And you could also imagine using it in upstream. Okay, so decision-making around exploration, where to drill, how to drill, both high-level decisions and low-level ones. If we had perfect RL, we could basically do anything that's physically possible. This is, of course, kind of a utopian vision. The situation in reality is not that easy. Okay? In the energy industry, typically the environments are super complex. It's very, very hard to have a model that's accurate and takes into account all the different factors that are relevant. Ambient temperature, degradation of equipment, interactions between different types of equipment. It quickly scales way beyond our mental capacity for mathematical modeling. Okay, and I'm sure many of you have seen this firsthand. Another problem is that trial and error usually is just unacceptable. Right? You're not going to let an algorithm make critical decisions that can cost extensive amounts of resources, can lead also to risks, not just financial, but also to people. It's dangerous, both from a safety perspective and from a cost perspective. It's usually unacceptable. So that means that both of the underlying assumptions behind standard RL methods are just not satisfied. So it's a problem. Right? Are we at a dead end? Probably not, otherwise I wouldn't be here. So the key to overcoming these difficulties, these challenges, in some cases, is data. Okay, I was taught in the first day of my PhD that the only thing better than data is more data. So just a kind of, my tip would be to always store data, even if you're not sure what you're going to do with it. And this is the case in many places in the industry. It's becoming more and more common to record data and to not compress the data in a lossy way. And that data paves way to a new approach for applying RL. And that approach is as follows. You first take the historical data and chop off of its sequences, and then you use self-supervised learning to learn a model of the environment. Okay, so over years of data, minute-by-minute data, the capacity of learned models, data-driven approaches, goes way beyond our ability to manually define a model of the environment. So a lot more can be picked up this way. And then, once you have this model of the environment, you train a controller through reinforcement learning, through trial and error, but the trial and error is virtual. It happens in the cloud. Okay, so safety concerns are pretty much non-existent. Cost is negligible. It's just a cloud compute. And then you have yourself a controller, and you can go and apply it in the real world. Okay, so this is the idea. And it's not just kind of an imaginary thought. It's something that's happening today. And this exact approach is what underlies process optimization across various parts of the industry today. This is what underlies Immubit's closed-loop neural network. There's a controller. Every minute or every 3 minutes, it takes an action. It moves valves, typically. It observes the state, the conditions of the plant, and it does so to maximize a reward, which usually reflects the margin. That margin can depend on constraints, upper bounds, lower bounds, or it can depend on parameters, that affect trade-offs like market prices and things like that. You turn the controller on, reward goes up. You turn it off, reward goes down. Okay? To connect this to the approach that we saw in the slide that was just before the last one, it operates as follows. You start by taking years of data, and through self-supervised learning, you learn a neural network, okay, that recreates the plant's dynamics. Okay, over years of historical data, then you take that neural network and you train on top of it a controller, which is also a neural network, and you do that through reinforcement learning over millions and millions of scenarios. Okay, this is equivalent to tens of thousands of years, because each scenario is not only defined by a certain point in time and the data that existed at that point in time, it's also defined by the constraints and the market prices that the controllers see. And these are generated randomly, so you end up with an potentially infinite amount of scenarios, and in this training, it's at least in the millions. All of this happens offline. Everything happens in the cloud. Then you take your controller neural network and apply it in real time to the environment, minute by minute control and optimization. This is what goes on there. It is very, very important to note that in reinforcement learning, and this is also relevant to AI in general, it's usually not going to tell you what you should tell it to do. Okay, you have to be very specific with what you want. And in reinforcement learning, the key way to convey your intent is through the reward function. And the reward is user-defined. Whatever it is that you defined, that's what's going to be maximized. Okay? So it's very important that all the different considerations are taken into account. All the different personas are taken into account in the definition of a reward function. Okay? And I think this is a lesson for AI in general. It's very, very important that all the different stakeholders weigh in the objective that is defined for the learned model. Specifically, in the case that we're talking about, the reward usually has two components. One are process constraints, like upper and lower bounds, and the other is some trade-off equation, usually an economic equation, It could depend on economic parameters like market prices. And kind of if I'm simplifying it, the reward would look something like this. If a bound is being violated, the reward is very low, like minus infinity, you could imagine. Otherwise, it's equal to the trade-off equation. So if a bound is violated, the controller focuses solely on resolving the bound. Once all bounds are resolved, the controller focuses on maximizing the trade-off equation, which again is usually an economic equation. All right, why are neural networks important? Why not use other models, linear models, or any of the other off-the-shelf techniques that exist out there? The reason is because neural networks are state-of-the-art in learning functions from data. This is proven time and time again over the last 15 years in various domains. The AI revolution that we are experiencing would never have happened if it weren't for neural networks. Everything that people use, that's state-of-the-art AI, is based on neural networks. Image, audio, text, everything. And this is not just an empirical observation. There are actually mathematical theories that explain this. Okay? I was personally fortunate to take part in some of these theoretical developments, and that's what I got the Google fellowships for. A note I wanted to make is that reinforcement learning without any trial and error, it has a name. It's known as offline RL, offline reinforcement learning. And it's something that is gaining a lot of attention from the leaders in the field, colleagues of mine, professors in Berkeley, Stanford, other places, the people that lead AI in Google, Facebook, OpenAI, et cetera. So it's getting a lot of attention, and it's because there are many safety and cost critical applications. Right? Outside the industry, the energy industry as well. For example, robot surgery, robots on Mars, or psychological therapy. These are places where you don't want algorithms doing trial and error. Right? And I just want to note that, to my knowledge, the closed-loop neural network that I just described is the first production-grade offline RL system. It's the first that I'm aware of. Okay? And still pretty much the only one that I'm aware of. This is running live on more than 70 applications today. Most of them started from refining, but now it's getting into chemicals, mining, minerals, solid fuels, also things like cement. In each application, the user defines a reward. That's what's being maximized. And this thing is having pretty significant impact on the industry. Okay? These are some of the organizations that use the solution. Some of the people here represent some of these organizations. Some of the models that have been running for over 5 years. It's running across dozens of plants in North America and other places in the world. And there's some testimonials here of the kind of impact that it had on people's facilities. All right, so let's conclude. So AI varies widely in how powerful and complex the machine learning framework that is in place. There's a joke that 3,000 years ago, X plus Y over 2 was called average, and today it's called AI. Right, so everything, if you know how to add two numbers, you can say you're an AI scientist. And I think it's exactly the same as saying that you're a technologist. If you know how to add two numbers, you're a technologist. It just means nothing. Okay? So the question is, what kind of AI, what kind of machine learning is taking place? There are various frameworks, supervised learning on the lower end, and other things, self-supervised learning, and on the higher end, it's reinforcement learning. Most of the applications in energy and in general are on the lower end, and on the higher end, specifically in reinforcement learning, there's a lot of unrealized value. Okay? Neural networks are state-of-the-art in learning functions from data. This is something there's mounting empirical evidence for this, and also mathematical theories that back this phenomenon. And the closed-loop neural network that I described applies neural networks for RL in process optimization. Okay? And it's the first production-grade offline RL system that I'm aware of. The ingredients are a neural network that's a learned model of the environment through self-supervised learning, a neural network that is a controller trained through reinforcement learning on the learned model of the environment, and a user-defined reward. This technology and RL in general will only be as good as your definition of the reward. Okay? It'll only be as good as the extent to which you faithfully formalize what it is that you actually want. Okay? And just a note about the future, this is in the context of the closed-loop neural network, but it holds in general for various solutions. It's very important if we want this technology to scale that users will be able to independently use it. And if it involves training models, they need to be independently training neural networks and obviously testing them and monitoring them. And it's not enough to just have the core AI algorithms, machine learning algorithms. The aspects of AutoML, which is the branch of machine learning concerned with allowing non-machine learning people to develop machine learning models, right? That and explainability are absolutely critical. You could have a perfect AI system if it's not explainable and if it's not something that users can use independently, it'll be very, very hard for it to scale. And I think in critical industries such as energy, these aspects are no less critical than the core algorithms that we want to deploy. Okay? So I talked about different AI frameworks and about reinforcement learning and its potential. Talked about an example for process optimization. There are many, many other use cases, and I hope that events such as this will foster collaborations and developments that will lead to the proliferation of reinforcement learning across the energy industry and make the world better. So, thanks.
Do we have any questions for Dr. Cohen?
Thank you. Have you seen any interesting cases of reward hacking in process optimization? Just some things that maybe surprised you.
So what do you mean by reward hacking?
Like there was a case where OpenAI published like one of their RL solutions for a game where, so you know, usually you define a reward function, pretty.
Okay, I think I understand what you're saying.
Right.
I think I understand. So what you're saying is that, if I understand correctly, what you're saying, there is a reward. The controller does what it's asked to do. It maximizes the reward, but does so in a non-sensible way. Or something like that?
Pretty much. Like usually there, for some scenarios there's a delayed gratification. So like you say like, hey, win at chess, but then, there's no, the reward is.
It definitely happens. It definitely happens. In the vast majority of cases, the conclusion is that the user did not define the reward well enough. Specifically at Immubit, there are kind of a lot of people coming from the industry and they know the user and they work with them. So it's an iterative process that happens. There are also situations where the user has defined what it wants, but reward hacking happens due to technical reasons. But these are things that are solvable, and over the years, every instance that we encountered was eventually solved. Things around delays, stuff like that, these are examples of things that needed to be addressed.
Hi, Dr. Cohen. This is Prabhu from Cognite over here. I got a set of allied questions, if you will. One is, you talked about the reinforcement learning being based on data. Industrial data is messy. Also, you might have the dynamics of the system is not just the pure physics dynamics, but also the dynamics of the controller, dynamics of the safety system.
Yep.
So do you ally this with any kind of physics simulator to understand the real dynamics of the system? Otherwise, you're also learning system inputs which are not real, which are actually based on human input. And on that as well, a lot of the times you have those safety systems in edge cases where it's difficult to predict, and that's why you have these other systems, right? Existing controllers do a pretty good job in the sweet spot of operation, but it's the edge cases that really bring you value. Yep. And if you have the system dynamics being augmented by other inputs, how do you then search that state space and control it? And the third thing is, what if things are changed in the system itself? Do you have to relearn everything? So a compressor is changed out and dynamics of the new compressor or the maintenance happens.
Yeah.
How do you handle that?
Yeah, okay, so this is a set of loaded questions, so maybe you should keep the mic because I'm not going to remember everything that you asked, but let me kind of try and you can remind me. So first of all, around the fact that the system might include control mechanisms or things like that, from our perspective, it's part of the environment. The environment does not have to be purely physical. In many cases, it includes things like APC and stuff like that. The data could indeed be messy. I didn't talk about this at all, but there's an entire platform with data cleaning capabilities and things like that. Okay. On your question around physics simulators, the way that this operates, this data-driven approach, there are first principles, but it's as opposed to more kind of traditional hybrid models in the industry, which are kind of first principle models with some parameters. Here it's a data-driven approach, and you can incorporate first principles, basically guide the learned model in its learning to respect things like mass balance, volume swell, things like that. It's part of the technology, and it's because in many cases, either the data is noisy or imperfect, or you don't have enough data, so it's definitely part of it. But still, from our experience, it is far more accurate than the opposite approach of starting with the first principles models and then having some parameters there or even a neural network inside there, because first principle models are usually based on assumptions that very, very often are not exactly satisfied in practice. And also, for example, if you look at the data and you check if the measured data satisfied things like mass balance, in many cases you see that it doesn't. And it could be because of measurement noise or things like that. But so the way we do it is we incorporate it in a softer way. Okay, so that was around that. Another question was, I guess...
the edge cases, right?
Edge
cases is where
okay, so neural networks, there are two types. This is a fundamental thing in machine learning. It's called generalization. That refers to the ability to generalize from the training data to the unseen data. There are two types of generalization, in distribution and out of distribution, which you can think of as interpolation and extrapolation. Neural networks are very, very good at interpolation. They also extrapolate to some extent, but there is no magic. Like if now the unit has moved to different conditions that have nothing to do with how they were, with what happened in the history, then the model is not going to be able to pick that up without additional knowledge embedded to it. So in these cases, a retraining with the newer data is going to be needed. The model does provide confidence. It does tell you if it's under conditions that are very different from what it has seen and it doesn't perform well on these conditions. But in the worst cases, you will need to recollect data. Usually starting from a few months, you can retrain, like 3 months or something like that. From our experience, it's very, very rare that the conditions of the unit are such that they have nothing to do with anything that happened in history. If they are a little bit outside the envelope but still related, you'll need much less than 3 months. I'm still not sure I answered everything, but hopefully that was enough and we can take offline.
Hi, good presentation.
Thank you.
There is a software company that creates a lot of seismic attributes using neural network, and I keep arguing them about the SOM. They call it self-organized map. From the get-go, 4 or 5 years ago, I said it's not a map, it's mapping, and you cover that. So you still think it's a SOM, self-organized map, or mapping? Mapping is a process. Map is a product.
Okay, so first of all, I'm not familiar with that particular company and solution, so I can't comment on that. If I
No,
project,
I understand.
I
It's
project
but, no,
what-
but you mentioned mapping, so it's a self-organized mapping.
I didn't say self-organized about in my talk. I guess the way I'm interpreting your question is it really something that works? Or does it really, the data-driven approach, does it really work? Or is there a person behind the scenes that does all the modeling? Is that the question?
It's okay. I know you mentioned it. It's in your talk, but it's a mapping process, not the self-organized map.
So we don't have we we have a two-phase process, learn
Right.
a model of the environment, do it on the cloud based on years of data. Then there is a model of the environment. You can test it. There's a platform. You can play with it, analyze, run what-if analyses. Once you feel comfortable with the model, you train on top of it a controller. A lot of trial and error going on, virtual trial and error.
Right.
It's in the cloud. It happens overnight. It's usually 10 hours, 12 hours. We keep it no longer than that. And then you test your controller, you analyze it, and after you feel comfortable with it, you deploy it online. So,
Okay.
yeah.
Thank you.
All right, thank you again, Dr. Cohen.
Thank you.
So much.